process integration, handling complex man-made networks, and the list go on. To his credit, Sir has received Best Virus Poster Award, Best Experimental Paper Award. Sir also has received Faculty Fellowship from Inspire. He has been expertise in the field of data science, data-driven modeling, optimization of bioprocess, big data in network biology, and also in the recent trends in the area which applicable to data science there. Sir, we, the faculty members and students are privileged to have you as our expertise to handle the session. Welcome you, sir. I hand over the session to you, sir.
Am I audible now? Hello?
Yes, sir.
Yes. Okay. Thank you. Thank you, ma'am, for a very generous introduction, and welcome all to this one hour session today. And I will also take another session on machine learning and data science next week or week after. So today I will talk about classification techniques. And before I go to the classification techniques, I will talk about two kind of problems which we deal with typically in areas of data science and AI, which we call it supervised learning techniques. Supervised learning techniques you can think of as a predictive techniques, where what we try to do is we try to take set of variables which we can measure and predict the output variable, which we call dependent variables, using some kind of mathematic formula, or what we call it functional relationships or relationship. And here, why it's supervised learning? Because when we try to build this kind of like machine learning models, we try to use what we call it label data. Label data in the sense that when you go to the doctor with the image and you look at that image of X-ray and say that this X-ray image has a small mild crack, and then that particular X-ray image has a label called it has some small fracture crack. And similarly, there is another X-ray image where there is no fracture crack. They will look at it and say there is no fracture. So now you have two images, and one image has a fracture, which is you already know that this image has a fracture. Another image you do not know has a fracture. And if you collect so much such a large amount of images, and you tell that, oh, this image has this fracture, this image does not have a fracture, then you have a huge amount of label data, because each time you have labeled these images. And the objective of any machine learning or data science project or course is to take these kind of images and build a model, so that when I have a new image where I don't know whether there is a this image contain a fracture or does not contain a fracture, I give it to my model and it predicts whether it has a fracture or not. And that what when we say there's a new image is called new instance of the inputs, or new instance of variable which I can measure and use that to predict the output, or typically it is a dependent variable. And in supervised learning techniques, there are two kind of problems we can solve. One problem where the output variable is quantitative. It can be continuous number or the ordered discrete output, or it can be a classification problem where we are not interested in giving a quantitative number, but just say that whether this image belongs, it has a fracture or not, right? That's a quantitative aspect, or categorical aspect, or qualitative aspect in terms of nominal or ordinal variables, or just you can say that, hello? So you can say that it is just a model which is going to predict yes or no or 0 or 1 kind of output given a set of inputs. So this looks bit strange. So let's take some examples. For example, in the case of healthcare industries, I uh, I want to predict time to recovery for COVID positive patients. So how long will it take the COVID patient to recover? So what I will do is I will go to hospital and I am going to look at the age of the patient, gender of the patient, loss of smell is there as a symptom or not, what is the saturation, O2 saturation, what are the variant which got by which is actually affected this particular uh, okay, uh, can excuse me, madam. Can you just mute the participant?
ఆమె రామంటే రాలేదు కానీ నేను తినేసి వచ్చింది ఈడున్న పడత హైదరాబాద్ ఏడ దొరకన్నా ఇక్కడికి వచ్చినప్పుడు ఇంకా ఇక ఇద్దరే చేస్తారా పీజీ ఏడ నువ్వు తెచ్చి
Okay, thank you. So, hello. Yeah. So the what you can do is you can measure a different uh, input features, what we call or attribute or other aspect of the COVID patient. And what also you know that in this particular case, when you because of course that this particular patient has recovered, so you know number of days to recover. Like what we call it target variable or response or dependent variable, which are all we call it out. Now I have a set of features, attributes, exploratory variables, and we have a set of what we have an output. And what my interest is, if next time a person comes in a COVID positive person comes and I have all these features, I want to predict how long will it take to recover for this particular person. And that helps me to understand a lot of interesting stuff about it because I know that okay, this person is going to admit for 12 days, 10 days, 15 days, 7 days, 22 days, etc. So this is a one example of a regression problem where I have an input and y and I want to build a model between the set of features and target. Let's look at bit other example, which is a finance, where I'm trying to predict delinquency of an individual. Again, I can have input features like age, income of that person, credit score, outstanding loans, etc. Many features, whether it's male, female, etc. And then I also look at whether this person has delinquency status or not. If it's yes, it is delinquented, then yes. If its delinquency status is no, then yes, no. And I can collect a lot of data like this. And now I have a set of input and set of output. What I'm interested in, again, the same idea, I'm interested in building a model when a new person comes. Okay, let's say I go and they'll ask what is my age, what is my income, what is my credit score, how many outstanding loans are there, and they want to predict what is likelihood of me being a delinquent. That is another. In case of marketing itself, again, the objective is I want to you basically in the online setting you look at many times you go to Amazon, look at products, and then you try to see whether you want to buy the product or not. Now, Amazon want to predict whether you will buy your product or not. So what they will do is they will use certain features like what device you are using, whether you are using what which is some kind of handheld device or PC, what kind of operating systems you have, what time you are using, what are the click, how many times you have clicked, whether you click advertise or not, what is the cookies, and also they will look at what is the cart status, you put something in cart or not. And based on that, you are going to predict this person is going to buy that product or not. So again, you look at this in this example, I am predicting yes or no. Similarly, in the finance, I am predicting yes or no. While in the case of healthcare, I am predicting a number. So when I'm interested in predicting a quantitative number, given x, what will be the y? It is a regression kind of problem, or it is called regression kind of supervised problem. While I'm only interested in predicting whether the output is in a quantitative nature, where yes or no, whether a person will be delinquent or not, or person will likelihood to buy a particular product or not, then I'm looking at a classification problem. Similarly, there's a lot of problems in engineering which deals with regression and the classification. One of the example is distance to empty in a car. So how long will it take to empty the car? So if I put a 5 liters of fuel, how long will it take? It will take what is the fuel utilization is that, whether it is a 12 kilometer per liter, 50 kilometer per liter, 60 kilometer per liter. And again, I'm going to use a set of features like fuel remaining, AC is on or not, number of passengers traveling in the car, temperature of the car, gear utilization. All these features are going to be used to predict the fuel utilization or mileage of the car. Again, here it's a regression problem because mileage is a number, quantitative number. So what I'm going to do is today I'm going to deal with one kind of problem, what I call it classification problem. And why classification problem? Because in many, as I told you already, there are two examples I have given, and I'll give you more examples. For example, fraudulent transactions on the credit cards. So if you look at it, whenever we buy certain things using credit card company have to figure it out whether the transactions you have made are genuine or fraudulent. If it is genuine transactions, it should be classified as a genuine transaction. If it's a fraudulent transaction, it should classify as a fraudulent transaction. And the company will look at many aspects about what you bought, where did you bought, what time you bought, what is the amount, etc., to predict whether it's genuine or not. Similarly, the doctors are interested given tumor, whether it's a benign tumor or it's a cancerous tumor. Or when you look at the industry, they are interested in given a quality of the product, whether it is acceptable or rejectable quality. So many times, as I told you, we can take a set of features and try to predict a qualitative aspect of that features, which is categorical in nature. The question is either yes or no, benign versus cancerous, fraudulent versus genuine, acceptable quality versus rejectable quality. All these are a qualitative nature of the outcome. And here, to predict this outcome, I'm going to use a set of features. And those features are typically measurable. If you recall, I talked about the X-ray image. In X-ray image, what you want to look at it is the following: that given X-ray image, I want to know there is a fracture or not, first equation, and look at also the location of fractures. So in that case, whether the image has a fracture or not, or whether the particular tumor image is a cancerous benign or not, that kind of problem are classification problems. And there are many other problems in a data science AI are meant to be are modeled as a classification problem. It is a technique, as I told you, is a supervised learning techniques, which is one of the larger class of the data science and AI kind of problem. So what does it mean by classification? So I have given here a simple figure where you can think of x1 and x2 denote some kind of features. Let's say weight and height. And using weight and height, I want to say that whether the person is a male or whether the person is a female. Okay? So blue one or blue dot indicates whether the person is a male, and yellow dots or yellow circles or zero indicate it's a female. And you can see there's a dotted line. And this dotted line is something which I want to discover using lot of data I have provided you for height, weight, and whether the person is a female or not. So here, what I want to do is, if I give you new height and weight, I want to ask whether this individual is male or female. This is called a classification problem. And typically classification uh, problems are of two class problems, which is we call binary class problems. And every time when we denote each class with a 0 or 1, or they can be multi-class problems. In a multi-class problem, I am interested in given height and weight. I want to predict that person is a male, female, or I want to also predict that, or I might be interested in given age and salary. I want to predict whether person is belongs to middle class or poor or rich or ultra rich, etc. In that case, I'm predicting a multiple class because given the age and salary, person can be uh, rich, ultra rich, rich, middle class, poor, etc. So there are 4 or 5 classes I'm predicting. And why we are interested in classification? Because as I told you, there's many tasks in the data science and machine learning belongs to that. In fact, every time when we walk, we drive, everything we use the classifications to solve the problems. If you go to uh, buy let's say potato or tomato, what you do is you pick up the tomato, you look at the different features of the tomato and decide whether it is a good quality tomato or not. Okay? We all do it when I go to the market. I also do it. Our mothers used to do it, and this is a very simple example. We do many tasks with our brain, which are in terms of classification. How should we drive, etc. Whether we should take left turn or right turn. All these are classification examples, and our brain use many features to do that. And in data science and AI, we want a machine to do the same. Only thing is that I have a nice eyes which I can use to figure it out. I have a hands which I can use to feel the let's say tomato and understand its quality and make a decision based on it, which I have learned from my parents. But my mother taught me, my father taught me that what is good quality tomato. Okay, sometimes I also learn from my experience. When I bought a poor quality, I realized that okay, next time I should not buy it. Any tomato with this kind of quality, I should not buy it. But how machine can learn? Machine has to learn through a data set, and we have to train. And hence, there are different type of classifiers because they use a different kind of techniques. If I talk with my mother, she said, okay, you look at this, look at the color, look at the firmness of the tomato, etc. And I asked my father, he said, no, no, you look at this other aspect of the tomato. So they both have their own way of making assumption about what good tomato looks like. And then based on that, they basically classify the tomato in the market and the buy the tomato. Same way, there are different techniques which use different kind of mathematical formulations and mathematical assumptions to classify or to perform the task of classification, which we call classifiers. And they have their own characteristic. For example, now naive-Bayes classifier use the concept of Bayes uh, classification or Bayes theorem. I think most of you know the Bayes theorem, which we studied in a probability, high school probability, conditional probability. And I'll talk about what is a naive here there. Similarly, there is a logistic regression or logistic classifier. K nearest neighbor classifier will say that, okay, I will look at uh, the features of K nearest neighbor and based on that decide whether this particular new point A belongs to the K. So on an average, uh, what I, uh, what I can do is I can take different kind of features and different kind of mathematical tricks to build a classifier. And these are all are basically nothing but a different kind of methods which use different mathematical formulations and different tricks to solve the classification problem. And I'll talk about some of them today. I'll start with a very simple one, which is called logistic regression. Here, the example I have taken is automotive crash test example. where I'm making taking features of the cars and trying to take a test and try to tell that whether the test testing is going to be a good or bad. So input features in logistic regression can be qualitative or quantitative. If inputs are qualitative, we can always convert them to quantitative by like saying, for example, if input is just or no or male or female, what I can do is, mm, if I have a yes or no, what I can do is I can say yes is equal to 1, no is equal to 0. Similarly, if I have a male or a female, I will say male is 0, female is 1, and that is called converting the qualitative variable to quantitative variable. Why we do this? One of the reasons is that it helps me to solve the problem with this logistic regression. So I can do that. So what is logistic regression? So now you think as a the following that each problem, as I told you, I have a set of X, which is my features, and then there is each feature has a label. So I'm looking at only two labels. The label is 0 or 1. The example of a product, whether given feature, the product is acceptable or it is not acceptable or reject. So let's say reject is 0 and features are and accept is 1. And this is the feature which basically tells you how to solve the problem in general. Now, if you look at it, this you can see that okay, I can make this simple line here and say below this anything is going to be 0, anything here is going to be 1. Right? This is a simple one. However, if you look at it, there is a sharp jump, and sometimes this jump happens cannot be found out that easily. There is a lot of challenges this jumps we have to handle. So if you think of this case, you want to maybe look at this kind of jump because in that case, or better one, if I can do this kind of curve, then I can solve given the feature. I have to predict what, and I can model this curve. Then I can given the x, I can always predict the y, and there is some threshold I can create which tells me that if it's below the threshold of I will predict it as 0, above this threshold, I'll predict it as a 1. So if I can do that, then it is fantastic because then in that case, I will have a perfect model. So how can we do that? So one of the way of solving this problem is that instead of predict y versus x, if I do some kind of conditional probability or expected value of y given x, or I call it simple logic probability. Basically, I'm going to log of this is called logic. So this is pi is a probability, which is conditional probability. Given the set of features, what will be the outcome? That's the probability that I'm looking for. It is pi, and since there are two classes, so this is let's say pi is equal to expected value of y equal to 1 given feature x. Then 1 minus pi will become expected value of y equal to 0 given x. Correct? Because total there are only two classes are possible. Then expected value of y equal to 0, given x is nothing but 1 plus, and the ratio of pi 1 minus called logit or logit, and here I am taking the log of it is log logit. Okay, and this probabilities I'm interested in modeling. So what I will do is I will model them as a beta 0 plus beta 1 into x. I know what is x, correct? I know that given x, what will be the probability of y is equal to 1, and what will be the probability of 1 minus 5. So it can be 0 or 1, and I can use this to create a problem. And this provides me an ideal S-shaped curve when I try to model given x given pi x. So if you remember, I talked about modeling this one and some kind of S curve where y is more like a probability of y with probability of pi of y, or sometimes it can be only pi. So how can we solve this problem? Pi of pi square. And what I'm going to do is I can use the logic function to create this S curve. And that's what I'm going to do here. And this particular model will provide me the this S function. The only thing which is going to be challenging is the following. What is going to be challenging? That uh, it will have two parameters, beta 0 and beta 1, and I have to somehow figure it out how to estimate beta 0 and beta 1. Right? It's not straightforward to get beta 0 and beta 1. Why? Because uh, uh, because this parameter has to be estimated from data. So how we can do this? We have to go further and estimate these two parameters using the data. Now, why? How can we do it? Because if I recall earlier, I talked about when I do build classifier, I have this X features and this out. So this is available to me as a data set. And what I can do is I can use this then to keep building a model. How can I do this? I will fit this X and use my probability to compute data to compute this probability and keep, keep predicting them. How can I do that? By fitting the model. And what I will get is this kind of function where I will get the beta 0 and beta 1 values. And I can, once I have these values by fitting the model, which is a simple linear regression, you can do it and fit the model. Once I have this model, I can use then for the new data x, beta 0, beta 1, I predict, or I don't have to use this one, I can directly use this one. and see whether it is near to 1 or 0, or I can use this itself to say that if it is here, I put it as a, when I'm in this region itself, I put it as a 0, and if I'm in this region, I put it as a 1. So uh, this pretty much about logistic regression. I can also do more formally. I can set up a likelihood function where I have this kind of objective function where y is equal yi is equal to 0 basically equals to xi, the feature belongs to class 0, and y is equal to 1 when xi belongs to class 1. And I can build a model, and I can also build this decision boundary, which is characterized by. So this is a bit technical detail, but what ultimately I'll get is a the boundary which I discussed earlier, which if you recall, that's uh, this boundary. This is what I'm going to estimate. This this is what ultimately gives this boundary. Now the question is why we want to use logistic regression. It is the simplest model I can build and interpret. Okay, because interpretation is one of the important aspects. How you can use classifiers and figure it out what are the important features which helps me to build a model. It works very well for binary class cases, and it provides very interesting prediction for the family of batting strategies. Similar scenario with the dimension Iitm next in the expense. Now, I talked about a simple logistic regression. I also wanted to talk about a bit more another uh, classification approach, which is basically is based on the Bayes theorem. Now, the simple question to all of you is, how many of you know Bayes theorem? I'm sure that most of you have heard about it in a probability. Am I right? Or you have studied when you were in the 12th standard or 10th standard. So this is very simple concept. And what we can do is we can use that concept uh, to understand a simple another classifier, which is also nice classifier called variable classifier. So here I I took a simple example where I have a bike name. This is a real data bike name. I have a whether the bike was got repaired or not, and the last column is whether the person was injured or not. And what we want to know is, given the data of accident report and the status is injured or not, I want to given let's say a bike name and it was repaired or not. I want to predict whether the person was injured or not in the accident report. So let's look at this same problem in a different manner and more better problem rather than let's not talking about accidents. Take about simple problem where I will give a weight and the engine cc. Okay. If all of you have driven some vehicle, I'm sure, some point of time in your life, and let's say you take a example of Activa. Hmm. What is the CC of Activa? If I remember correctly, it is around 120 or something. Right? CC is basically engine size, and what is the volume of engine, and the weight will be around 100. But many of these bike or motorbikes, they have a little bit later weight, but they have a high engine CC. So I have given here for the 4 Yamaha bikes weight and engine, and Honda weight and engine. And what I'm interested in is the following. I'm interested in predicting, given weight and engine, what is the type of bike, whether it's Yamaha or whether it is a Honda. Now, if I look at the data here, which is I have, this is my data has been that I have a 8 data points. Data points. And if I look at them together, I realize that 4 of them are for the Yamaha and 4 of them are for the Honda. And if I use this data, then I can say that, okay, if I randomly choose any bike, don't worry about weight and engine, I choose randomly, the probability of being a Yamaha is 1 by 2 or 1 by 2 or 0.5. Similarly, the Honda also has the same thing. And typically, this is the probability where I don't care about weight and engine. I don't have information of weight and engine at all. When when I go further and I look at the weight and engine, what I'm interested in predicting what is a bike type. Okay. Uh, for example, here I have given you weight equal to 85 and engine CC equal to 250. I want to know whether it is a Yamaha bike or it is a Honda bike. Okay, that's what I'm interested in, whether it is a Yamaha or it is Honda. And I want to use this data. That's something. And I want to use the base theorem, which I have studied during my high school. That's why I like this classifier. It does not require any knowledge beyond a high school. And you can still build a good classifier. Of course, if you want a more complex problems, you need to learn some advanced tools, but it's still grounded in a very simple concept which we studied during our high school called base theorem. So what we let me again go to the more formally the naive-Bayes classifier, where I have this red and the blue color, which indicates certain classes, and I have this one here is a x2 and x1, which are my features, and I want to come up with some kind of classifier which tells me when the new point has come whether it is blue or red. So what I'll do is, what I have is, I have two features as I told you, x1 and x2. Okay, and I want to predict whether it is a red or violet. Okay, red or let's say red or violet or blue. So if you recall conditional probability which we studied, this is probability of whether it is red or violet given x1 and x2 can be written as probability of x1 x2 given the either red or violet, into the probability being a red divided by probability of x1, x2. This is a simple conditional probability formula which we have studied. If you want to think of it is from the our thing, this is the A is an event which is either the the class being a blue or red, or and the B is giving B can you can think of as a feature which has happened, which is some set of x1 and x2. Then I want to predict given B, I want to know whether what is the probability of A. The same way I am doing it here also. The only thing here is the following, that unlike conditional probability we studied in the high school, I have to make a decision by computing two probability, one for the probability for R, another is the probability for violet, given the same features, and I have to make a decision. Typically, when we studied in the high school or first year of our college, we typically get, okay, it is probably compute the probability of A given B. I'm going to do following. I'm going to compute the probability of A given B and compute probability of some A dash given B, and then say which one is a higher probability and make a decision out. So think this way: if I want to take a umbrella or not, or jacket or not, what I'll say that okay, let me go outside and see whether the event which I say that whether the uh, uh, the sky is covered with the clouds or not. If sky is covered with the cloud, that's my probability B. Then I want to predict the A is whether uh, uh, whether whether okay, whether it is going to rain or not. So if it's the probability of A being the rain is the one probability, probability A being the not going to be rain is another probability. Both are given that there is a cloud, there are clouds in the sky, and then whichever probability is higher will decide that it is going to rain or not. And if it's going to rain, then I am going to take a umbrella with me. Okay? The same thing we are going to do is the only thing is that we are going to compute this probability. We are going to use Bayes theorem, which we have studied when we studied in the probability in high school. So let me talk about probability of orange, red given x1, x2 is proportional to probability of x1, x2 given red into probability of red. Recall that this is kind of same for red and violet. So we are currently replacing this equal sign with a proportional sign. Now I'm going to make a simple assumption, which are often called a naive assumption. Okay. So what I'm going to assume that this x1, x2 are independent features. So I'm going to assume that if I have some features, the x1 will not provide information about x2, x2 will not provide information about x1 in some sense. Then I can write them as a probability of x1 in these two probability together is nothing but probability of x1 given red into probability of x2 given red. Why I am doing this? Because this probability is easier to find using the data I have actually collected. So I'll just ignore these things and just talk about the simple example where the data we have collected. What I did is I computed the mean of the weight, mean for the engine, variance for the weight, and variance for the engine using the data which has been given to me. Okay, this data. Why I'm doing it, I will talk about it sometime. What I'm interested in is computing this. Remember this all the. Let me clear it. What I'm interested, as I told you earlier, I'm interested in computing this probability and also interested in computing the probability. Let's say what will be the probability of, sorry, then it will make sense. If you given x1, x2. Okay. See, this is just for a uh, uh, to make a decision, not just for a completion. I'm saying that I'm interested in computing this probability, this probability. Similarly, here I'm interested in making a or computing a probability or making a computation such that probability of Yamaha given the weight and engine, probability of Honda given a weight and engine. Right? Now, to compute these two, I'm going to use a Bayes theorem, which I have discussed earlier. So this Bayes theorem will boil down to probability of Yamaha into probability of weight given y Yamaha into probability of engine given y Yamaha into 1 by probability of x and y. This is basically the denominator which I told you that going to be same in both cases. Here similarly probability of h given x can be written as probability of h into probability of weight given h, probability of engine given h. Now probability of y and probability of h, probability of bike being Yamaha and probability of bike being Honda brand, we already know from the data which remember I have already computed. This is my first probability, this is my second probability. So I know that. So I don't need to worry about because I know. However, to compute these probabilities and these probabilities, these probabilities, and these probabilities, I have to come up with some way. So I have to use my data. And what simple assumption I'll make it is that this data is drawn from some Gaussian distribution. In other words, Gaussian distribution, I know the form. This is the form for the Gaussian distribution. Here, probability of x equal to y given c is equal to 1 by 2 pi sigma c square into e raised to minus mu c by 2 sigma c square, right? Where mu c is a sorry, given the bike type, what will be the my mean of this distribution and what will be my variance. For the variable of interest, the variable of interest here is weight and the engine. For Yamaha, so given Yamaha as a bike, what will be the probability of being the weight? You can actually compute using the data available here. And I have done that. And I have computed this probability. What I have to do is then I have to multiply all this probability. You can go and do this analysis at home. Okay. And or maybe when Rituraj and Roshan talk about different models, they will also discuss this particular kind of distribution classifier. And you will see that here when you compute it, you see the probability of Yamaha is greater than probability of Honda. Then I can say that for what? For the when I give a weight equal to 85 and engine equal to 2250 cc. If I do that, I have this uh, particular observation to make where I say that probability of Yamaha given this weight and engine cc is greater than probability of Honda. And then I can say that okay, I have to make a decision whether this particular weight and engine cc belongs to which bike. Since the probability of for Yamaha is higher, I'll predict that this bike is definitely Yamaha. This is basically tells me that by using simple probability, I can compute a class probability for two class problem, and I can solve the problem. This particular aspect can be generalized to a multi-class also. So I'm not going to talk about more detail, but if you have rather than having a only Yamaha and Honda, you can have a Suzuki, you can have a Harley Davidson, all kind of bikes. And then you given that CC, you want to predict which class, which type of bike you have. And you can formally same analysis can be formalized for a multi-class problem. So uh, what I will do is I will conclude with these two uh, models. There are many other models, something called K nearest neighbor models, which again can be used to decide whether the uh, uh, particular new features belongs to which class. And this is one of the simple classifier based on the similarity of its neighbor, and the K talks about how many neighbors. So what you can think very simply about yourself. So if you are in particular school, particular college, or particular age, I talk about those things and then predict that if I put someone near to you, I assume that if new person comes to your class, he or she would have a same kind of characteristic as you have, same kind of degree they have. So the K here is the number of neighbors, and how many neighbors I have to choose is a kind of hyperparameters, or what we call it, has to be decided by fitting the models. But it is just look at the similarity between my nearest neighbor and decide whether I belongs to which class. So probably whether I belong to class one or class two. So there are many other classifiers are there, such as I'm not going to talk about them today. So I would like to conclude that the classification is an important class of problem. Roshan and Rituraj will talk about different kind of classifiers. I'm hoping that they will at least teach you logistic regression, neighbor-based regression, KNN regression, neural and neural network classifiers. Uh, uh, and what you will do is implement some of these classification techniques on hands on different kind of problems. So it will give you a feeling that, okay, if I have to solve certain problem, where given the features, I have to predict which class it belongs to, or which quantity, whether it is fraudulent versus genuine, accept or reject. I can actually do that given the data. Next week, I will talk about regression problem also. I'll take 1 hour and discuss about regression problem and some testing problem. If you have any questions, I can answer. Sorry. Anybody has a questions, they can raise your hand or put it in the chat and I can answer. So, madam, actually, madam, if there are questions, I can take it. Otherwise, I will give a next lecture next week. Maybe same place.
Thank you, sir. You have a normal formal vote of thanks, sir.
Yeah. Thank you,
Good
madam.
evening.
Yeah.
Good evening to all. It's my privilege to propose a vote of thanks on behalf of Department of Computer Application, Sri Meenakshi Government Arts College for Women, Madurai. First of all, I thank Almighty for gracing His occasion in smooth online learning without any interruption. At this juncture, I would like to thank our respectable principal, Dr. Vanandi Madam, for her constant support and encouragement in organizing this program. I thank our beloved head, Department of Computer Application, Ms. Rajarajeshwari Madam, for her consistent execution of this program continuously for more than 3 years, that in turn benefits our student community in large. Thank you, ma'am. I thank all our faculty members of computer application for their active involvement. Thank you all. Especially, I take this opportunity to thank our eminent resource person, Dr. Nirav Bhatt, Program Chair MTech in Data Science and Artificial Intelligence. Sir, thank you so much for sharing your expertise in the field of supervised learning. Sir, you have given a clear-cut explanation of regression and classification scenarios through real-time applications such as healthcare, through finance, marketing, and engineering. It's really very useful for us as a beginner. Thank you, sir. Sir, we got exposed to different types of classifiers to solve the classification problems. And also we learned the working of a logistic regression clearly through your simple explanation. So thank you so much. And sir, and also through our simple example, we also got through the how a classification can be done more effectively through our Bayes theorem and also naive Bayes classifier, and also through different kind of classifier. To initiate, it's really very helpful, sir. In the coming session, we are eagerly waiting to listen more. In turn, we benefit, we want to do more with in data science, sir. So thank you so much, sir, and spending your valuable time with us. I would like to thank each and every one of you through which the program is being organized there. And also I thank all the faculty members and the student participants who have been actively involved in this session for their learning in data science, sir. I thank one and all gathered here. Thank you, sir.
Thank you, ma'am. Thank you very much. And I hope that people as Roshan will teach more detail and hopefully far better than I do. Yeah, thank you for your time. So, and I'll give one more lecture on regression if is needed. I'll coordinate with Professor Raji and Roshan and Raji. Thank you everyone for your time. And if you have any questions, you can ask. I can understand a little bit of Tamil, so if you are because it's a ask in English, I heard from Roshan that there was quite a bit of questions. Tamil, so if you want, I can ask in Tamil also next time. Okay. Yeah. Thank you, everyone. Have a nice evening, and it was wonderful to meet you folks. And maybe we'll.
Thank you so much, sir. Thank you. Thank you so much.
Thank you, sir.
Thank you. Have a nice evening.